Good evening, everyone. I hope I'm audible. So today we have successfully reached the fourth day of our ATAL FDP. It is sponsored by AICTE Training and Learning Academy. And as we all know, our FDP has its thrust areas on artificial intelligence and data science. The title of our FDP is Emerging Trends and Applications in Artificial Intelligence and Data Science. So here we have gathered here for our 7th session. And our resource person is here with us today. Her name is Reshma KM, and she holds a diploma in data science and has an experience in this field for over 10 years. She started off her career as a data science intern at Edathala. And after working there for 1 year, she gained some practical experience and exposure. And then she moved to Futura Labs, and she has been working there for quite some time now. She is not just a data scientist, but she also trains professionals and students in areas like data science, machine learning, deep learning, business intelligence tools, etc. So she is a very apt person for our class today because she is someone who has experience both in the academia as well as industry. So we are indeed really fortunate to have her with us today. I hope that the session can be really enriching because we have a very informed person to lead us today. I welcome the guest, Reshma ma'am, to the session wholeheartedly on behalf of our entire college, MESMK Mackar Pillay College. I hope that we can make best use of this session. Now I invite ma'am for the session. Without any delay, let's start our very first session. She will be talking to us on the topic unsupervised learning. So ma'am, over to you.
Thank you.
You can start, ma'am.
Hi everyone, I am Reshma KM. I am a data scientist and as well as a data science trainer at Future Labs. I am really happy with you today. Let's start our session. Today our session is about unsupervised learning. I will explain everything in a simple and easy way with real life examples. It will help you to understand easily. Let's start. Everyone can see it, right? Am I audible?
Yes, ma'am, you're audible and we can see the presentation as well.
Okay. First, we will go through what is machine learning. We live in an age where technology is everywhere. From the moment we wake up until we go to bed, we are surrounded by machines, gadgets, and applications. Our phones reminds us of meetings. Apps recommend music and movies. Banks send us alerts. And then navigation apps guide us to our destination. What makes all this possible is not just fast computers, but smart computers. These computers are no longer limited to doing only what we program them to do. Instead, they are able to learn from data and experiences, just like humans do. This smartness of computers comes from a field called machine learning. In simple words, we can say machine learning is teaching computers to learn patterns from examples and experience instead of only following fixed rules. What is machine learning? Traditionally, we can say computers follow step-by-step instructions given by a programmer. For example, If we want a computer to calculate 5 plus 5, we tell it add 5 and 5. It follows the instruction and gives the answer 10. But what about problems that cannot be written as simple formulas? For example, we can make a computer recognize a photo of a cat. How can we make it predict whether it will rain tomorrow? How can we make it recommend the best movie for us? These are not problems with direct formulas. Instead, they require learning from patterns in data. Machine learning allows computers to do exactly this. Machine learning is like teaching a computer with examples, so it can make smart guesses on its own. In simple way, we can say it's like teaching a child. Imagine you are teaching a child to identify mangoes and apples. At first, you show them many mangoes and apples, telling them the names. Slowly, your child notices the patterns. Mangoes are usually yellow or green and oval. Apples are red or green and round. Next time, when they see a fruit they have not seen before, they can guess whether it is a mango or apple. Machine learning is just like this. Instead of a child, we have a computer. Instead of fruits, we give it data like images, text, numbers, etc. The computer learns patterns from the data and then makes prediction on new data. Machine learning may sound like a new topic, but it has been around for decades. In 1950s, computer scientists started thinking, can a machine learn like a human? In 1959, Arthur Samuel, a pioneer in AI, used the term machine learning while teaching a computer to play checkers. The computer learned by playing many games, like that, improving over time. In 1990s, with the rise of the internet, more data became available. Machine learning started being used in spam filters, search engines, and recommender systems. In 2000s and beyond, with smartphones, social media, and huge amounts of data, machine learning became a daily part of our lives. Today, without realizing, we use machine learning almost every hour. In our day-to-day life, we are using machine learning. Examples like entertainment, travel, healthcare, in every sector, we are using machine learning. In entertainments like we are using in YouTube, Netflix, Spotify, etc. When you watch action movies on Netflix, the system remembers your interest. If you continue watching similar movies, it learns that you like action. Next time you open Netflix, it will recommend more action films. Similarly, YouTube suggests videos similar to what you usually watch. In shopping like Amazon, Flipkart, Myntra, when you search for shoes, Amazon not only shows shoes, but also similar products related to shoes. Because why? Machine learning has learned from millions of customers that people who buy shoes often also buy related products. There were another examples like travel, email, voice assistants, etc. Voice assistants like Siri, Alexa, and Google Assistant. When you say play music, Alexa understands you. The more you use it, the better it understands your accent and favorite songs. In banking sector, machine learning is used for fraud detection and loan approval. Banking, if your card is always used in Kochi, but suddenly a purchase happens in Mumbai, the bank's machine learning system alerts you. Banks also use machine learning to decide loan approvals by studying past data. In healthcare like diagnosis and scans, doctors use machine learning for detect dataset in X-rays, CT scans, or blood reports. For example, detecting early signs of cancer by finding patterns invisible to the human eye. We can next see how machine learning works. Let's take a daily life example. Using predicting house prices, we can see an example. First, we collect data. Next, train the model and test the model and improve the model. If collecting data means gather informations like house size, number of rooms, locations, etc. Next, we train the model. Train the model means feeds this data into the computer. The computer learns patterns. Next, it gives new data. It means testing the model, like a house with 3 rooms, and see what the computer predicts. And next, improve the model. If the predictions are wrong, give more data and train again. It's like exactly like preparing students for exams. First we study, next we writing exams. After the exams, we learn from the mistakes and improve. There are mainly two types of machine learning algorithms. There are supervised learning and unsupervised learning. In yesterday's session, we already covered about supervised learning. Supervised learning is a computer is given data with answers. For example, show pictures of cats and dogs labeled correctly. The computer learns to tell them apart. For example, Gmail spam filter. Emails labeled like spam or non-spam. Unsupervised learning is a computer is given data without answers. It groups them on its own. For example, we are going to shopping. Shopping data without labels. The system groups customers who buy similar products. There are another one learning include reinforcement learning. It means the computer learns by trial and error, getting rewards for correct actions. For example, a robot learning to walk. If it fails, no reward. If it walks, it will get reward. For example, self-driving cars learning to drive safely. These three are the main of machine learning, and we are mainly focusing on unsupervised learning. Next is advantages of machine learning. Machine learning saves time. The computers can analyze data in seconds. It improves the experience. The more data, the smarter it gets. It used for better predictions. From weather forecast to cricket match analysis. Machine learning is used for personalized experience like Netflix, YouTube, Instagram, etc. It will also used for automation. Tasks like spam filtering, fraud detection, it will happen automatically. Next is disadvantages and challenges. It needs a lot of data. Without enough data, it performs poorly. It will get errors and wrong predictions. Sometimes machine learning systems make mistakes. It will also getting privacy issues. Since machine learning uses personal data, it will get misuse is possible. Expensive in some cases. Building advanced machine learning systems requires high computing power. These are the challenges occurred in machine learning. There are many fields we are using machine learning like healthcare, education, agriculture, finance, etc. In healthcare like detecting diseases, drug discovery, personalized treatments, all of these sectors we are using machine learning. In education, smart learning apps, exam predictions, personalized lessons, etc. In agriculture field, it will helps to predicting weather, crop diseases and soil health, etc. In transportation like self-driving cars, smart traffic signals, route optimization, and in the entertainment like music or movie recommendations, content creation, etc. Next, we will discuss about future of machine learning. The future of machine learning is huge. We can expect smarter personal assistants that act like real humans. Hospitals where machine learning predicts diseases before symptoms appear. Fully driving cars that reduce accidents. These are the future of machine learning. Next, we are going through our main topic, unsupervised learning. When we think about learning, the first picture that comes to our mind is usually a teacher in a classroom. The teacher gives us notes, explains the topic, and checks whether our answers are right or wrong. This is a very guided learning process. In computer science, this type of learning is called supervised learning because the computer learns with the help of supervision or labels. Am I audible, right?
Yes, ma'am, you're audible.
Okay. But in life, we don't always learn with teachers or ready-made answers. Many times we learn by simply observing patterns around us. For example, you move into a new neighborhood. Nobody tells you who is friends with whom. But by watching, you notice that certain families often meet each other, some kids always play together, and some groups prefer different activities. Or when you enter a supermarket, nobody explains where things are, but slowly you observe and figure out. Fruits are in one corner, drinks are in another, and snacks in another. This is the natural way of finding patterns without being taught directly, is exactly what computers do in unsupervised learning. Unsupervised learning is a type of machine learning. Unsupervised learning is when a computer tries to learn patterns, groups, or hidden structures from data without being given the answers. It is like giving a curious child a box full of mixed toys and watching how they organize it on their own. The children's mixing up of boxes, they made different boxes, like cars in another, blocks in another, without anyone telling them how to do it. It's it in a computer, it's like unsupervised learning. Next, what is unsupervised learning? In supervised learning, we give the computer both the question and the answer. For example, we are giving an input like photo of a cat. We are giving label it as a cat. Photo of a dog. We are giving label as a dog. But in unsupervised learning, we only give the input, not the answers. Input like photo of cats and dogs without labels. The task for computer is to look at patterns like shape, color, and size. It will groups them on its own. It's like saying, here is a big basket of fruits. I won't tell you which is apple and which is mango. Just find the similarities and group them. This makes unsupervised learning very important in real life because in most cases, data is not neatly labeled. For example, millions of shopping bills, photos, or customer records are not categorized. Computers need to figure it out themselves. In simple way, imagine a new teacher enters a class of 50 students for the first time. She doesn't know their names, grades, or interests. At first, everything looked mixed. But after a few days of observation, she started noticing patterns. Some students always sit together and whisper. They are friends. Some students are very quiet while others are very active. Some love sports, some love reading. Without anyone telling her, she is able to group students into categories. This is unsupervised learning in real life. The idea of unsupervised learning is not new. It is started in the early days of artificial intelligence. In the 1950s to 1960s, scientists wanted to see if computers could discover hidden patterns on their own. Early techniques like K-means clustering were introduced, where computers grouped data into clusters, like students groups into clusters. In 1990s, with the rise of the internet, huge unorganized data like email, shopping, music became available. This made unsupervised learning important for grouping and organizing. Today, with social media, online shopping, we are using unsupervised learning is everywhere. Next, we are going to types of unsupervised learning. There are two types of unsupervised learning, clustering and dimensionality reduction. Clustering means grouping similar things together. For example, grouping customers in a shopping mall. Group A buys luxury items. Group B buys budget products. We can say in a real life example as Google Photos grouping faces of same person automatically. It's a unsupervised learning. Dimensionality reduction. Making big data simpler by reducing unnecessary details. For example, from a 100-question survey, removing less important questions while keeping main data. It like compressing photos so they take less storage but still look good. We can say it in a daily life examples like supermarket and shopping. When you shop at a supermarket, your bill is stored. Thousands of bills are collected every day. By studying them, unsupervised learning finds patterns like people who buy milk often buy bread. People who buy chips often buy cold drinks. This helps the store place products together in increase sales. Online shopping like Amazon, Flipkart, Myntra. These sites are unsupervised learning to suggest items. If you bought a mobile, they suggest mobile covers. If you search for shoes, they recommend socks, etc. Banking sector or finance, banks use unsupervised learning to detect fraud. For example, if you usually spend 5,000 a month but suddenly spend 50,000 in another city, the system marks it as unusual. Credit card companies group customers into big spenders, savers, travel lovers, etc. In healthcare sector, doctors use unsupervised learning to group patients by symptoms. For example, patients with mild fever and cough, they are group A. Patients with high fever and breathing difficulty, they are group B. This helps in quick treatment. In education field, online learning apps group students into categories like fast learners, average learners, and slow learners. This helps teachers personalize lessons. Social media platforms like Facebook, Instagram, Twitter. When Instagram shows you ads for products you never search for, it's because it grouped you with people who have similar interests. For example, imagine opening a kitchen drawer full of mixed items like onions, tomatoes, biscuit, chocolate, etc. Without being told, you separate them into groups: vegetables, snacks, grains. This is unsupervised learning at home. This is a simple real life example. Next is Netflix. Netflix has millions of viewers worldwide. It doesn't ask viewers to fill forms about what movies they like. Instead, it studies what you watch, at what time you watch, whether you finish a movie or stop halfway. By grouping viewers with similar habits, Netflix creates categories like comedy lovers, thriller fans, etc. This helps it recommend movies and increase watch time. Amazon like doesn't know each customer personally, but it studies millions of shopping bills. It finds relationships like people who buy laptops also buy laptop bag and mouse. People who buy baby product also buy diapers. This association rule helps Amazon suggest product and increase sales. In healthcare during COVID-19, during the pandemic, doctors had huge amount of patient data. Unsupervised learning grouped patients into mild cases, severe cases, and critical cases. This grouping helped in deciding who needed urgent hospital care and who could recover at home. Next is advantages of unsupervised learning. Unsupervised learning, no answers needed. It saves time because we don't need labeled data. It finds hidden patterns. It can discover things humans might miss. It can handle big data, useful for large amount of unorganized information. We can use it for real-time benefit, for like fraud detection, live recommendations, etc. Exploratory like helps researchers find new insights using unsupervised learning. The main disadvantages of unsupervised learning are it not always accurate. It may group things incorrectly. Hard to interpret. Sometimes the results don't make sense. It needs high computing power. For very large data, it can be costly. Patterns may be useless. Not every discovered pattern is meaningful. In unsupervised learning, the future looks like very exciting. Smarter assistants like Siri and Alexa will understand us without retraining. In healthcare sector, diseases may be detected before symptoms appear. Smart cities like traffic, electricity, and waste can be grouped and managed. In education sector like each student will get personalized learning paths. In robotics, we can say robot will learn on their own without needing pre-labeled training. In simple words, we can say unsupervised learning is a teaching computers to explore and organize things on their own without giving them the correct answers. As data continues to grow in our world, unsupervised learning will play a huge role in making our daily life smarter, faster, and more personalized. Next is there are two types of unsupervised learning in clustering and dimensionality reduction. In clustering, there are two types: hierarchical clustering and partition clustering. Partition clustering is also known as k-means clustering. First, we can see clustering. Clustering is one of the most powerful and widely used techniques in machine learning, especially under unsupervised learning. The word cluster simply means a group. For example, we talk about a cluster of islands in geography, a cluster of stars in astronomy, or even a cluster of friends in a classroom. In the same way, in machine learning, clustering means grouping similar items together. But here is the interesting part: the groups are not predefined. The computer is not told in advance whether something is an apple, an orange, or a banana. It just receives a lot of data and then it tries to group similar things together. This is very much like real life. Think about when we are children. If someone gave us a basket of fruit but never told us their names, we could still sort them into piles. All the apples in one pile, bananas in another, oranges in another. We didn't need labels. We only used our eyes to notice color, shape, size. That's exactly what clustering does. And why do we need clustering? Before going deeper, let's ask, why do we even need clustering? Can anyone know? Okay. The world is full of information. We generate data every time we shop online. watch a movie, scroll through social media, visit a doctor, or even walk with a fitness tracker. But most of this data does not come with clear labels. Nobody is sitting and writing, this customer is a tech lover. This patient has mild fever. Yet, if we want to use data effectively, we need to find groups and patterns. Clustering helps in exactly this. It gives us a way to make sense of large amounts of data when we don't have labels. For example, business can group customers into budget buyers, luxury buyers, and occasional shoppers. Hospitals can group patients into high risk, medium risk, and low risk. All this grouping happens without any labels. This is the magic of clustering. In daily life, clustering is an example. Let's see some simple everyday examples of clustering. It makes the concept clear. In every classroom, small groups of friends naturally form. Some groups love sports, some love books, some love movies. Teachers don't assign these groups. They happen naturally. That is clustering. Another example, wardrobe organization. Without thinking much, we keep formal clothes in one place, casual wear in another, and traditional outfit separately. That is clustering too. In travel groups like in a tourist place, we see groups of families, groups of friends, and group of solo travelers. Without a guide telling us, we can easily recognize the clusters or groups. In our WhatsApp group also, our WhatsApp chats are clustered into family, office, friends, and study groups. This is the clustering. Clustering is something our human brain does all the time without even realizing it. Machine learning simply tries to imitate this process. Next, we can see how does clustering work. We can see it by step. Suppose you give a computer 1,000 pictures of fruits. You don't tell it which one is an apple, orange, or banana. You just say, here are some pictures, find the patterns. The computer starts analyzing features. Apples are usually round and red. Bananas are long and yellow. Oranges are round and orange in color. Slowly, the computer notices similarities and divides the picture into three groups. One cluster of apples, one cluster of banana, and one cluster of orange. Notice that the computer did not know the names. It only grouped them by looking at the similarities. Later, we as humans can give names to the clusters. This is exactly how clustering works. I think these real-life examples help you to understand the concept clear. Next is types of clustering. There are two types of clustering. I already told K-means clustering and hierarchical clustering. K-means clustering divides the data into K clusters. K-means clustering is the most common clustering method. Imagine dividing students into class into three groups based on the height. First one is short, second one is a medium, and last one is tall. You random. It is called centroids. In clustering, here the leaders in clustering it is the centroids. Each student joins the group of the leader closest to their height. After a while, the leaders shift to the average height of their group. Slowly, the group stabilizes into three clear clusters. K-means is simple but powerful. Next is hierarchical clustering. This builds a tree of clusters. This method works like building a family tree. First, each person is their own cluster. Then the two closest people form a pair. Those pairs join other pairs, forming bigger groups. Finally, you end up with a full tree showing how people are connected. For example, in a wedding, people may first stand with close cousins, then merge into larger family groups, and finally into one big family. Next is applications of clustering. Clustering is everywhere around us, even if we don't notice it. Here are some real life examples. Customer segmentation in business, recommendation systems in healthcare, banking, social media. First of all, we already told about healthcare, banking, social media in unsupervised learning. In clustering also, these are the examples. In customer segmentation in business are online shopping sites like Amazon, Flipkart. It will group customers into clusters, gadget lovers, book readers, fashion shoppers, etc. This helps in sending personalized offers. Recommendation systems like Netflix groups users into clusters like action movie fans, comedy lovers, drama watchers, etc. This is why your recommendations differ from your friends. In healthcare sector like doctors use clustering to group patients with similar symptoms. For example, grouping diabetes patients into high risk, medium risk and low risk categories. In banking sector, banks cluster customers to find potential loan defaulters or to design special offers. In social media like Facebook and Instagram, cluster users into groups with similar interests for targeted ads. In education sector, teachers can cluster students into fast learners, slow learners, average learners. This helps designing better lessons. In astronomy also, scientists cluster stars and galaxies to study the universe. Next is advantages of clustering. It helps discover hidden patterns, works even without labels, useful in large datasets. It makes recommendation and prediction easier later. Disadvantages of clustering are the computer may form wrong clusters if data is unclear, and choosing the right number of clusters is tricky. Different algorithms may give different results. Let's imagine a new student joins a school. The teacher don't assign her to any group. She sits quietly and observes. Slowly, she joins the group of students who play football because she also likes football. She is now part of the sports cluster. That's clustering. Finding your natural group without being told. In simple words, we can say clustering is grouping similar things together without knowing their names beforehand. It is one of the key building blocks of machine learning and an important step toward making computers think more like humans. In k-means clustering, the algorithm flow is like first we give in input, that means data. Next, it processes the data and after that, finally, we are getting output. Next is k-means clustering. Here, we are mainly focusing on k-means clustering. One of the most famous and widely used clustering methods in machine learning is k-means clustering. It is also known as partitioning clustering. The name itself may sound technical at first, but if we break it down, it means there are meaning in each word, like K means K means the number of groups or clusters we want to form. Next is means. It refers to the average. Average means mean point of each cluster. Clustering means grouping similar items together. So in short, we can say K-means clustering is a method of dividing data into K groups, K number of groups, where each group is represented by its average point. It is simple, powerful, and used in a wide range of real-world problems like customer segmentation, market research, and even organizing photos on your phone. We can say it is a real-life example. Imagine you are a teacher and you want to divide your class into 3 groups based on the height. Short students, medium height students, tall students. How will you do it? First, you randomly pick 3 students and make them group leaders. Then every student looks at which leader they are closest to in the height and joins that leaders group. Now, instead of keeping the original leaders, you make the average height of each group the new leader. Students again check who they are closest to and join that group. This because continues until no student feels the need to change groups. Finally, you end up with 3 clear groups of short, medium, and tall students. That is exactly how K-means clustering works. I will explain step by step of K-means. Choose the value of K. Decide how many clusters or groups you want. For example, K equal to 3. It means 3 groups. Next step is initialize the cluster centers. It is the centroid. Randomly pick K points from the data set as a starting centers. These are called centroids. In step 3, assign points to the nearest centroid. Every data point looks at the centroids and decides which one is closest. It joins that cluster. Next, it recalculates the centroids. After forming clusters, calculate the new average position. It means mean of all points in each cluster. This new average becomes the new centroid. Repeat this step. Again, assign points to the nearest centroid. Again, calculate the new centroid. Continue until clusters stop changing. At the end, we get stable clusters where each point belongs to the group whose centroid is nearest. For example, in simple, everyday situations where K-means is happening around us. In supermarket customers, a supermarket may want to divide its customers into 3 groups: budget shoppers, mid-range shoppers, premium shoppers. K-means can help find these groups based on purchase, amount, and product preferences. In mobile phone photos, your phone automatically groups your photos, families, friends, and nature. It separates these 3 photos automatically. It doesn't know the labels but uses clustering techniques like K-means to organize. Apps like Spotify or another music apps. Users are grouped into clusters like pop lovers, jazz lovers, rock lovers, etc. Recommendations are given based on your cluster. Education like students can be grouped into fast learners, average learners, and slow learners based on their marks. In healthcare section, patients can be clustered into high risk, medium risk categories based on their symptoms. Next is advantages of K-means. In simple and easy to understand and implement. Works well even with large dataset. It means it is user very fast. Useful in many fields: business, healthcare, education, social media, etc. K-means is flexible. It can handle different types of data like age, marks, spending, etc. Disadvantages of K-means are it needs to choose K in advance. We must know the number of clusters beforehand. Sensitive to starting points. Different random centers may give different results. Not good with uneven clusters. If groups are of very different sizes, K means struggles. Sensitive to outliers. One odd data point can shift a centroid wrongly. For example, imagine we have data of fruit based on the weight and sweetness. Apples are medium weight and medium sweetness. Bananas are heavy and very sweet. Grapes are light and sweet. If we set K equal to 3, K means will form 3 clusters: apple, banana and grapes. Even though we never told it the names, it grouped them correctly. Later, we can label them as fruits. Next is applications of K-means. In real world, we can use K-means in market segmentation, documentation classification, image compression, social media analysis, in healthcare, etc. In market segmentation, companies divide customers into clusters to send better advertisements. In document classification, like news articles can be grouped into sports, politics, technology, etc. Image compression means K-means reduces the number of colors in an image, saving storage. Social media analysis clusters users by interest for targeted ads. In healthcare, grouping patients with similar symptoms for diagnosis. Think of a school playground. The teacher says, children, please form 3 groups. At first, children randomly pick a spot and form rough groups. Then they notice some groups are too close and adjust. Slowly, children settle into 3 stable groups. This playful activity is exactly like K-means clustering. In short, we can say K equal to number of groups, means equal to average point of each group. K means equal to grouping items into K clusters. Using their average values, it is widely used in business, education, healthcare, technology, and more. That's why K-means is considered the starting point for learning clustering algorithms. In K-means clustering, just walk through our code. First, import our libraries. Next, create the data and apply the K-means. Next, plotting the clusters. Here we are importing sklearn and import load iris. Load iris, iris is our data set. It is already a built-in data in the sklearn. Next, we importing pandas. These are the Python libraries. From sklearn, cluster import k-means, and matplotlib also the library. Next, we create data. Load the iris dataset and create data frame. After that, we are applying here the k-means algorithm. I will show a demo of this code. Everyone can see this slide? Visible, right? Okay.
Yes.
Okay. Okay. This code demonstrates the practical application of the k-means clustering algorithm using the popular iris dataset. with the aim of identifying the optimal number of clusters through the elbow method. The data set, which contains measurements of sepal length, sepal width, petal length, and petal width, is first loaded and structured into a pandas data frame for ease of analysis. The k-means algorithm is then applied iteratively for cluster sizes ranging from 1 to 10. For each value of k, a k-means model is trained and the inertia value is recorded. Inertia refers to the sum of squared distances between each data point and its assigned cluster center, serving as an internal metric to access clustering quality. These values are then plotted against the number of clusters to produce the elbow curve. The significance of this curve lies in its ability to help us determine the most suitable number of clusters by observing the point. It means the elbow point, where adding more clusters to no longer result in a significant reduction in inertia. This method provides a simple yet powerful visual tool to guide clustering decisions, making it highly relevant in data science and machine learning applications. Here, from sklearn.dataset, import load iris. From import pandas as PD. This is the library we import. Here we import the iris dataset from sklearn.dataset and also import pandas for handling data in tabular format. Next, we give a variable iris and load iris. This loads the iris dataset into the variable iris. This dataset contains measurements of iris flowers, features like petal length, sepal length, etc., along with species labels. Next, we created a data frame, pd.dataframe iris.data. It converts the dataset into a data frame with proper column names like sepal length, sepal width, petal length, and petal width. This makes the data easier to view and manipulate. Next, we import matplotlib.pyplot as PLT. This is for the visualization. Matplotlib is the visualization library. Next is inertia. Here we giving inertia. It creates an empty list inertia to store inertia values for different cluster sizes. Next is for k in range. It starts a loop for cluster numbers k from 1 to 10. We will test clustering with different number of clusters. K means equal to K means number of clusters equal to K, random state equal to 0. Here we are giving this. It creates a K-means model with K clusters. Random state equal to 0. It ensures reproducibility, same results every time. Next we are giving K-means dot fit. It fits means trains the model. The K-means model on our iris dataset. This assigns each data point to the nearest cluster. Next is inertia.append. It after fitting or after training the model will take the model's inertia value. It means sum of square distance from each point to its cluster center and store it in the inertia list. Next, we are plotting the k-means. Plot the number of clusters 1 to 10. 1 to 11 means 1 to 10. On the x-axis against the inertia values, on the y-axis the marker we are giving O. It adds a dot for each data point. Next we are giving x label, y label. X label number of clusters, y label inertia. It adds the label to the x-axis as number of clusters and y-axis as inertia flow clarity. Next we are giving plt.grid. If we are removing plt.grid, we can't see this grid line. If we need, we can give, or otherwise we can remove. Next, plt.show. It displays the plot, giving us the elbow curve, which helps in deciding the optimal number of clusters by finding the elbow point. If needed, I will show it. If I am removing this plt.grid, it will remove these grid lines and we got this plot. This is the best method because we are giving grid, we can see this elbow method. Here we can see the dot or points. This is mainly unsupervised learning. Now we can just revise the topic. First we discussed about machine learning. Machine learning is all about teaching computers to learn from data instead of giving step-by-step instructions. In everyday examples like Netflix recommend movies, email filter spams, Google Maps predict traffic, etc. Think of it like teaching a child by showing examples rather than telling them every rule. Unsupervised learning is a type of machine learning where the computer learns patterns without being given the answers. We only give the data, no labels. Example, grouping customers by shopping habits. In clustering, it's a way to group similar things together in unsupervised learning. The computer looks for similarities and divides data into clusters. For example, sorting fruits into apples, oranges, etc. It's like grouping students based on the learning speed. Types of clustering include k-means and hierarchical. In k-means, it groups into k clusters using averages. In hierarchical, it forms clusters like a tree, small to large. In k-means clustering, it is the most popular clustering algorithm. Its steps are choosing the k number of groups, pick random centroids, assign points to the nearest centroid, and recalculate the centroids. Repeat until groups stabilize. For example, grouping students by height, customer segmentation in stores. It like children naturally forming groups in a playground. Applications like shopping apps, Netflix, Spotify, healthcare, social media, education, etc. These are we discussed about unsupervised learning and machine learning. From this whole session, the main points we need to note that are machine learning helps computers learn from the data. Unsupervised learning finds patterns without labels. Clustering groups similar items together. K-means is a simple and popular way to cluster into K groups using averages. In simple words, we can say machine learning helps computers learn. Sometimes we guide them supervised. Sometimes we let them explore. It is unsupervised. Clustering is one way to explore and K-means is a popular method to group things smartly. Do you have any queries? Okay, can you explain elbow method? Elbow method is a technique used in clustering, mainly in unsupervised learning, to find the optimal number of clusters in algorithms like k-means. Imagine you have some data points and you want to divide them into groups or clusters. If you try different numbers like 1, 2, 3, 4 and so on. For each number of clusters, you calculate a value called within cluster, sum of squares, which is basically measures how close the points are to the center of their group. If you plot the number of clusters on the x-axis and on the y-axis, the graph will look like a decreasing curve. The elbow at first. When you increase clusters, it drops a lot. But after a certain point, adding more clusters doesn't improve things much. The graph starts to flatten. This turning point looks like a elbow in your arm. That is the elbow method.
Madam,
The
screen is
point
not shared. Madam, screen not shared. Now it's okay.
Okay. Okay. That point, the elbow is usually the best number of clusters to choose. Do you have any another queries?
Hello, madam.
Yes.
Madam, what are the performance measures for the clustering?
What?
Which are the performance measures for the clustering?
Performance measures of clustering.
Yes.
Okay. Performance measures. When we do clustering, the algorithm groups similar data points together. But unlike supervised learning, we usually don't have labels to directly check accuracy. So we use performance measures or evaluation metrics to judge how good clustering is. There are mainly two types: internal measures, no true labels available. These use only the data and the clustering result. They check how compact and well separated the clusters are. Measures how close each point is to its own cluster versus other clusters. It will range from -1 to +1. +1 represents the well clustered. 0 is the overlapping clusters. -1 is the wrong clustering. Next is external measures. External measures means true labels available. If we know the actual classes, we can compare them with the clusters. Compares how many pairs of points are clustered correctly. It also range from -1 to 1. For each cluster, check the most common true label. Purity means correctly assigned samples or total samples. It will range from 0 to 1. It combines the precision and recall for clustering. Next is relative measuring. It compares two clustering solutions. Example, k equal to 3, k equal to 4, etc. to decide which is better. Often used along with internal measures. Anything else? Okay. I think queries are over.
Ma'am, there is one more query in the chat box.
Okay. I will stop this sharing. Otherwise, I can't see the chat box.
It's okay, ma'am. I'll read it out. Ma'am, the question is, it is from Mala H. Mehta. She's asking, I don't know if it is I don't know if I'm pronouncing the name right, or I don't know if I'm pronouncing the pronoun right. I'm sorry. But the question is, please explain performance measures practically. Yeah, please explain performance measures practically.
Performance measures.
Yes, ma'am.
Okay. I will tell one more example. Clustering students by study habit. Suppose we have 10 students and we measure only hours studied per day. Student studies hour like A1, 1 hour, 2 hour, like that. Clearly, there are two natural groups. Cluster 1 like low study, 1 to 3 hours are lower study, and 8 to 10 hours are higher study. Internal measures are no labels needed. Fill out score. For student A, studies 1 hour. Average distance to its own cluster. It's are small. Average distance to other cluster. It's close to 1. They are good at studying. If a student studied 5 hours in between, it would be near 0, confused cluster. If a student studying 1 hour accidentally went into cluster 2, it is -1. It is very bad. For cluster 1, students are very close. For cluster 2, students are close. If we made 3 clusters instead of 2, would be even smaller. That's why in elbow method, we check where it stops, decreases sharply. External measures, if we know true labels. Suppose teacher already knows students are actually low study versus high study. We can compare our clusters with true labels. External measures, I thought if we know true labels, it is purity, adjusted rand index, NMI. NMI means clusters share all information with true label. Relative measures like perfect match with true groups. Splits high study group unnecessarily. It improves but purity drop. In simple words, we can say students are close to their own group than others. It is silhouette measures. And next is WCSS. It tight are the groups. And next is purity. Do clusters match teachers groups? Next is relative. Which number of clusters is better? I will show in a screen. Wait.
Hello, ma'am. Are you there?
Yes, yes. I will show
Okay,
it.
okay, ma'am. Take your time. Take your time. I was wondering if you lost network. Yeah.
Everyone can visible this.
Yes, ma'am. Yes, ma'am. It is visible.
It's just an example for we have 10 students and we measure only hours studied per day. A one student studied 1 hour, B and 2, like that. It will internal measures needs no needed of labels and external measures if we know true labels. In internal measures, there are two methods, SIL-out score and WCSS. SIL-out score means student A studied 1 hour, is very close to its own cluster and far from others. A student at 5 hours would have SIL-out. It means confused. Wrongly placed student would give -1. And WCSS measures compactness. Cluster 1 is tight and cluster 2 also tight. More clusters reduce WCSS. It is used in elbow method. Next is external measures. If we know the true labels, it will give the purity, adjusted rand index and NMI. Both clusters perfect match true groups. Next is all pairs correctly grouped, that are 1. Clusters shall all share all information with true labels. I think another one question is in chat box. Production in agriculture.
Yes,
In,
ma'am. Yes, ma'am.
in unsupervised learning, it finding patterns in data without label. In agriculture, it can be used like this. Clustering group farms of crops based on the soil, water, climate and yield. For example, high yield farms, medium yield farms and low yield farms. We are using dimensionality reduction. Simplify large farm data like soil, mineral, field, fertilizers, rainfall, etc. into fewer main factors to understand production better. A farm producing very low yield may be pest attack. A farm producing very high yield may be new method. In simple words, we can say unsupervised learning helps farmers and governments see hidden groups and patterns in farming data so they can improve production, give better support, and plant crops wisely. Okay.
Are there any other queries, guys? Any other questions or doubts? If you have, please unmute yourself and ask. You can ask. I think there are no more queries, ma'am. Ma'am?
Any other queries? Okay, so let's wind up this session. I sincerely thank MES College for this opportunity to be part of this faculty development program. On behalf of Future Alert, I am grateful to have contributed to such a meaningful initiative. It has been a wonderful experience interacting with you, all of you, and I truly appreciate the efforts of the organizers and participants in making this program a success. Thank you.
Thank you so much, ma'am. It was indeed a very good session. You explained about unsupervised learning in a very simple yet effective way. I especially liked how you used so many examples from our daily life, which made it so relatable. And we could understand the concept in a much broader way. For example, how you talked about Google Photos and how it clusters photos with similar faces. It was really interesting how you use such examples. Thank you so much, ma'am. It was a very light-hearted yet very informative session. Thank you so much. I express my sincere gratitude on behalf of MES MK Mackar Pillay College for Advanced Studies. Thank you so much, ma'am.
Thank
It
you.
was indeed a pleasure. Thank you, ma'am. You can take a break. Thank you. I would like to remind the participants that the feedback form has been pasted in the chat box. The link has been pasted in the chat box. So please access the link and fill out the forms so that we can mark your attendance. Please do not leave without filling the So our first session is over and our next session will begin at 7:30. So you can go and take a break and be back at 7:30 sharp. And I want to remind you again that the feedback forms, the links of the feedback forms has been pasted in the chat box. So please access the link and fill out the forms now itself. Yes, Shankadeep, you have 10 minutes. You can be back by 7:30. Hello, dear participants. I apologize for that trouble. Hello, dear participants. I hope all of you are back after the short break. Now we have successfully completed the first session and we are moving on to the second one, for which we have our resource person here, Aisha Fina ma'am. She's already familiar for us because she already took a session yesterday. She is a data science trainer, over 10 years of experience in the field of academia as well as industry. And she has a strong background in BSc statistics, and that gives her an edge in the data science industry. And she is also a trainer, and she has worked in so many firms, training so many individuals in areas like machine learning, business intelligence, etc. And she's indeed a very uh, rich resource person for us to have with us here today. I invite ma'am for the second session. She will be engaging with us on the topic hierarchical clustering. So I hope all of us can take use of this opportunity. I want all the participants to listen carefully and be diligent listeners. So I invite you, ma'am, for the session. Ma'am, are you there? Hello, ma'am.
Yes.
Okay, ma'am. So shall we start the session?
Yes.
Okay, ma'am.
Hello everyone. My name is Aisha Fina. I'm working as a data scientist. I specialize in Python programming, data science, machine learning, and another Python technical. So we can start. Today, we are going to explore an exciting concept in machine learning called hierarchical clustering. Clustering is one of the most powerful techniques in unsupervised learning. It helps us find hidden patterns and natural groupings in data. For example, imagine you are a teacher with a large classes of students. Uh, I hope everyone can hear me, right?
Yes, ma'am, you're audible.
Okay. Just imagine you are a teacher with a large class of students, and you don't know the performance level yet, but you have the exam marks. Without setting categories like top scorer, average, or low performer beforehand, how can we naturally group these students, right? That's where clustering comes in the algorithm. Hierarchical clustering is type of clustering. Clustering, what is mean by clustering? Clustering is one of the most important technique in unsupervised machine learning. It's about grouping data points in such a way that points in the same group are similar to each other and points in different groups are dissimilar. Clustering is the process of dividing data into groups like clusters based on similarity or distance. Just a real life example, like In shopping mall, grouping customers based on purchase habits, luxury buyers versus budget buyers. In healthcare, grouping patients by symptoms for better diagnosis. In another example, like Google News, automatically grouping news articles about the same event. Just another example as in social media, suggesting new friends by grouping similar profiles. Think of a classroom where students naturally from groups, toppers, average students, and those who need extra help. That's clustering in real life. Why we need clustering? Just we can say to discover hidden patterns in data. To simplify and summarize big data into meaningful groups. To enable targeted decisions, example like personalized marketing, to act as a pre-processing step before other machine learning algorithms. How does clustering work? We can say we define a similarity or distance measure, example like Euclidean distance. The algorithm groups data points so that intra-cluster similarity high and inter-cluster similarity low. High means points inside a cluster are close. Low means points across clusters are far. An example, in a 2D scatter plot of students, marks in maths and science, clustering groups them into high performance and average performance and low performance. There are many types of clustering is there. One is partial method like k-mean. First one is k-mean. K-mean is predefined number of clusters, algorithm assign points. Second one is hierarchical method. It is build clusters step by step, agglomerative and divisive. There are two types of hierarchical methods are there. One is agglomerative and other one is divisive. The third type of clustering is density based. It is groups dense region of points and detect outliers. Clustering is grouping similar data points without predefined labels. It's widely used in marketing, healthcare, text mining, and biology. Different algorithms exist, but all have the same goal: discover patterns and group data meaningfully. So coming to hierarchical clustering. Okay, we will discuss about what is hierarchical clustering. Hierarchical clustering. Hierarchical clustering is an unsupervised algorithm. Hierarchical clustering is an unsupervised algorithm. What is unsupervised algorithm? Unsupervised algorithm, just imagine you walking into a library with thousands of books, but none of them are labeled by category. We can't organize them, right? We might notice patterns. Some books like novels, some are technical, some are magnetized. Then that's exactly what unsupervised learning does. It finds hidden structures in data without labels. Unsupervised meaning it finding hidden structures in data without labels. In supervised learning, we have labeled data like marks as grade. In unsupervised learning, we only have raw data with no labels. The goal is to find patterns, groupings, or relationship automatically. Example, clustering. Clustering is grouping customers by buying behavior and grouping students by mark. Hierarchical clustering is an unsupervised clustering, avoids the need to decide on the number of clusters. as in the case of k-mean clustering. It's a distance-based based algorithm as the case of k-means clustering. So coming to hierarchical clustering, why we using hierarchical clustering means hierarchical clustering is combines use hierarchical clustering to groups customers based on their purchasing behavior, spending patterns, or demographics. Example, an e-commerce site like Amazon can cluster users into groups such as frequent buyers, discount seekers, and premium customers. Helps in targeted marketing and personalized recommendations. Second example, like hierarchical clustering is widely used in natural language processing. Example, Google News groups similar news articles together by topic. Documents are represented as vectors, and clustering helps organize them into themes like polities, sports, or technologies. Third example, why we are using hierarchical clusterings. It's a biological data. In biology, hierarchical clustering is used to classify genes with similar expressions patterns or to build physiological trees. Example, like in genomics, scientists use it to find which genes behaves similarly under certain conditions. Also used to create to showing how different species are related. So there are two types of hierarchical clusterings there. One is agglomerative hierarchical clustering. It is good at identifying small clusters. Second one is divisive hierarchical clustering, good at identifying large clusters. Hierarchical clustering is a tree-based clustering algorithm that builds a hierarchy of clusters. Its key features, unlike k-means, it doesn't require you to redefine the number of clusters. Start small, merging into large groups, it's agglomerative. Start big, split into small groups, it's divisive. Produces a dendrogram, a tree-like diagram that shows how clusters are formed step by step. Just an example, think if for in the family tree, think in our family tree, at the bottom, each person is an individual, right? As you go up, you see parents, grandparents, etc. Merging into bigger groups, that's exactly what hierarchical clustering does, building a family tree for your data. Yeah, what is hierarchical clustering is? Agglomerative hierarchical clustering is two types of hierarchical clustering is there, agglomerative hierarchical clustering and divisive hierarchical clustering. Agglomerative hierarchical clustering is each point start as its own cluster. Agglomerative hierarchical clustering is good at identifying small clusters, and each point starts as its own clusters. At each step, the closest clusters are merged, and the process continues until all points are in a single cluster. Hierarchical clustering is two types: agglomerative hierarchical clustering and divisive hierarchical clustering. Agglomerative hierarchical clustering means in agglomerative hierarchical clustering, each point start as its own cluster. At each step, the closest clusters are merged. Process continues until all points are in a single cluster. And coming to divisive hierarchical clustering, this is the second type of hierarchical clustering, divisive hierarchical clustering. Good at identifying large clusters. It starts with all points in one clusters. Agglomerative hierarchical clustering, each point start as its own cluster. In divisive hierarchical clustering, start with all points in one clusters. It split the clusters step by step, separating furtherless points. Continue until each point is its own cluster. Two types hierarchical clustering. One is agglomerative hierarchical clustering. Each point start as its own cluster, and at each step, the closest clusters are merged. Process continues until all points are in a single clusters. Coming to divisive hierarchical clustering, it starts with all points in one cluster. It splits the cluster step by step, separating furthest points. Continue until each point is in its own cluster. Agglomerative is merging, divisive is splitting. That's the difference between agglomerative hierarchical clustering and divisive hierarchical clustering. Agglomerative hierarchical clustering is type of like a merging, and divisive hierarchical clustering is splitting. Agglomerative is merging, divisive is splitting. Just like example, like suppose we have 5 students with marks. In agglomerative, each student is first a separator cluster. We merge closest marks step by step. When coming to divisive, we start with all 5 students in one group. Split the group until everyone is separate. That's a difference. Example as I said, suppose we have 5 students with mark. Just imagine, suppose we have 5 students with marks. And coming to agglomerative hierarchical clustering, each student is first a separate cluster. Each student is first a separate cluster. We merge closest marks step by step. And coming to divisive, we start with all 5 students in one group. Split the group until everyone is separate. Hierarchical clustering is an unsupervised tree-based clustering algorithm. It builds clusters step by step, either bottom-up agglomerative or top-down divisive. Bottom-up is agglomerative, top-down is divisive. It gives us a dendrogram, which makes it very visual and easy to interpret. Types of hierarchical clustering. First one, agglomerative hierarchical clustering. Second one is divisive hierarchical clustering. Both methods aim to build a hierarchy of clusters, but they differ in how they approach the process. One builds bottom up, the other one is top down. When coming to agglomerative hierarchical clustering, its definition is also called bottom-up clustering. Agglomerative clustering is also known as bottom-up clustering. How it works? Firstly, it starts with each data point as its own cluster. When coming to agglomerative hierarchical clustering, it's also known as bottom-up clustering. It working first, it starts with each data point as its own clusters. Start with each data point as its own cluster. The second step is merge the two clusters that are closest together. Start with each data point as its own clusters. Secondly, it's merge the two clusters that are closest together. It will repeat until only one cluster remains. It will repeat until only one cluster remains. The key point in agglomerative hierarchical clustering is it's good at identifying small tight clusters. Agglomerative hierarchical clustering is good at identifying small tight clusters. Just an example like a student with marks. Suppose student score is, just imagine, 45, 47, 85, 90, 92. Student score is 45, 47, 85, 90, 92. The first step is each student is a cluster. In hierarchical clustering, each student will be the clusters. Each student is a cluster. Second step is merge closest scores. In my example, 45 and 47 are closest and 90 and 92 are the closest scores. It will merge closest scores, 45 and 47 and 90 and 92. And coming to step 3, it keep merging until one large cluster is formed. The dendrogram shows this merging visually. Think of forming a WhatsApp group. Just think of forming a WhatsApp group. First, two friends will the most in common start chatting. Then they add others step by step until the whole class is in the same group. That is hierarchical clustering. The second one is divisive hierarchical clustering. And coming to divisive hierarchical clustering, it's defined as also called top-down clustering. Divisive hierarchical clustering is also known as top-down clustering. How it works? It starts with all data points in a single cluster. Divisive hierarchical clustering start with all data points in a single cluster. Secondly, it split the clusters into two groups based on the furthest points. It continues splitting until each point is its own cluster. Working of hierarchical clustering is, firstly, it starts with all data points in a single cluster. Secondly, it split the cluster into two groups based on the furthest points. Thirdly, it continues splitting until each point its own clusters. Its divisive hierarchical clustering is good at identifying large, broad clusters first. For example, you can say, for an example, think of a company, we can think a company. You start with one big department, then split into small teams, and finally into individuals. The comparison is between agglomerative and divisive. Coming to agglomerative, bottom up, it's a bottom up, merges small clusters into good for small detailed groups. In coming to divisive, it's a top down, splits large clusters into good for broad grouping first. Both gives us a dendrogram. Agglomerative and divisive both give us a dendrogram, but the construction process differs. Use agglomerative when you want to detect fine-grained small clusters. We can use agglomerative hierarchical clustering when we want to detect fine-grained small clusters. We can use divisive hierarchical clustering when we want to start from a big picture and drill down. That's the difference between agglomerative and divisive. We can use agglomerative hierarchical clustering when we want to detect fine grains, small clusters. We can use divisive hierarchical clustering when we want to start from a big picture and drill down. Similarly, agglomerative hierarchical clustering is a bottom-up approach where each data point starts as its own cluster, and the closest clusters are merged step by step until one large cluster remains. In divisive hierarchical clustering, it's a top-down approach where all data points start in a single cluster, and the cluster is split step by step until each point stands alone. And shortly, agglomerative is merge small into big, divisive is split big into small. Agglomerative is merge small into big, and divisive is split big into small. So moving on. Agglomerative hierarchical clustering, also called additive hierarchical clustering. It's merged the closest pair of clusters at each iteration and repeat this until a single cluster itself. And coming to divisive hierarchical clustering, it works the opposite way. It starts with a single cluster with all the points in it. The furthest point in the cluster are split in each iteration until each cluster contains only a single point in it.
Shari, please mute yourself. All the participants, please mute yourself so that ma'am can take the class properly. You can
Okay.
continue, ma'am.
Okay. Once again, agglomerative hierarchical clustering is it's a bottom-up approach where each data point starts as its own cluster, and the closest clusters are merged step by step until one large cluster remains. That is agglomerative hierarchical clustering. And coming to divisive hierarchical clustering, it's a top-down approach where all data points start in a single cluster, and the cluster is split step by step until each point starts alone. Similarly, agglomerative is merged small, converting into big. In coming to divisive, it's split big into small. Okay. In this slide, it is explaining agglomerative hierarchical clustering. One of two main type of hierarchical clustering is also known as bottom-up clustering. Agglomerative start with each data point as its own cluster. Then in each step, the algorithm finds the two clusters that are closest and merge them together. This merging process continues until eventually all points are combined into a single cluster. Why it's called additive? it is something called additive hierarchy clustering because we keep adding merging clusters step by step. Thinking of it like building a group chat. First individual starts alone, right? Then two people join. The group merge until everyone is in one big chat. The explanation of the diagram at the top of the slide, we can see individual data points, each assigned as the separate clusters, shown as small circles. Then the closest points are merged. For example, two nearly circles are grouped. Gradually, more points get merged into large groups. At the bottom of the diagram, you can see multiple clusters inside bigger circle, representing the step-by-step merging process. Finally, all points fall under one large circle, one cluster. The bottom-up approach works well for identifying small, tight clusters. It uses a distance or similarity measures like a Euclidean distance to decide which clusters to merge. The result is shown using a dendrogram, which we will see in later slides. To summarize, agglomerate hierarchy clustering begins with individual data points, merge the closest one step by step, and finally forms one big clusters. Bottom-up additive approach that is especially good at finding small detailed clusters. In this slide, assigning points to individual clusters looks for the smallest distance in the proximity matrix and merge the points with the smallest distance. Now that we have created a proximity matrix that stores the distance between every pairs of students. Let's see how the agglomerative clustering process actually begins. At the start, each student is treated as an individual cluster. You can see here that student 1, 2, 3, 4, and 5 are all shown as separate points with different colors. The matrix shows pairwise distance. For example, distance between student 1 and student 2 is 3. Distance between student 1 and student 3 is 18. Distance between student 4 and student 5 is 15. The smaller the value, the closer the students are in terms of marks. Notice how the diagonal is 0 because the diagonal is 0 because the distance from a student to itself is always 0, right? The diagonal values are 0 because the distance from a student to that student, a student to itself, it's always 0. That's why the diagonals are 0. The algorithm looks at the matrix and identifies the smallest non-zero value. The algorithm looks at the matrix and identifies the smallest non-zero value. In this case, the smallest distance is 3 between student 1 and 2. Smallest distance is 3. That means student 1 and student 2 are the most similar pair in terms of marks. Student 1 and student 2 are the most similar pair in terms of marks. In this case, the smallest distance is 3. That is between student 1 and student 2. Smallest distance is 3. That means student 1 and student 2 are the most similar pair in terms of marks. So, in the first step, we merge them into one cluster. The first step is, firstly we check the smallest distance. In this case, the smallest distance is 3. That means student 1 and student 2 are the most similar pairs in terms of marks. So in the first step, we merge them into one cluster. That's our first step. We merge them into one cluster. On the right side of the slide, you can see how this looks visually. On the right side, you can see how this looks visually. At first, all 5 students were separate circles, right? All 5 students were separate circles. After the first merge, student 1 and student 2 are joined together into a single cluster, while 3, 4, and 5 remains as individual clusters. After the first merge, student 1 and 2 joined together into a single cluster, while 3, 4, and 5 remain as individual clusters. 1 and 2 are together into one cluster, and remaining 3, 4, 5 and 3, 4, 5 are in individual clusters. This process will continue in the next step with updated distance. It will continue in the next step with the updated distance. This step is very important. Why? Because this is a foundation of agglomerative clustering. This step is very important because this is the foundation of agglomerative clustering. We always start by finding the closest pair and then gradually merge until only one big cluster remains. We will start by finding the closest pair. We will start by finding the closest pair and then gradually merge until only one big cluster remains. Every step of merging will later be represented, that is dendrogram. Just recap of previous step. In the previous step, we merged student 1 and student 2 because their distance was the smallest, 3. Now, instead of treating them as 2 individual points, we treat them as one cluster, 1, 2. In the previous step, we merged students 1 and 2 because their distance was the smallest, right? Now, instead of treating them as 2 individual points, we treat them as one cluster. This means our data set now has only 4 clusters. 1, 4, 1, 2 is one cluster, and 3, 4, and 5 are individuals. 1, 2 becomes 1, and 3, 4, 5 are individuals. So in our data set now have only 4 clusters. After merging, we need to recalculate the distance between the new clusters. We already merged our data set, and after merging, we need to recalculate the distance between the new cluster and all other clusters. You want to recalculate the distance between the new cluster and all other clusters. But how do we measure this distance between cluster that contain multiple points? There are 3 common linkage methods: single linkage, minimum distance, complete linkage, maximum distance. Average linkage means mean distance. The choice of method, 3 linkage methods are the single, complete, and average. Single is minimum distance, and complete is maximum distance, and average is mean distance. The choice of method affect the final shape of cluster. The choice of which one want to choose, single linkage, complete linkage, or average linkage. The choice of method, it affect the final shape of the cluster. Yeah. Coming update the proximity matrix. The marks can be filled using the minimum and maximum or average of the value. In here, on the left side, you can see updated table of student. On the left side, we can see the updated table of students. 1, 2 into 10, 3 into 28, 4 into 20, 5 into 35. Student ID is 1, 2, its mark is 10. Student ID 3, its mark is 28. Student ID 4, mark is 20. Student ID is 5, the mark is 35. Here, 1, 2 is shown as a single cluster, right? 1, 2 is shown as a single cluster and its mark is 10. The updated proximity matrix, on the right side, we can see a new proximity matrix. We can just read it. A distance between 1, 2, and 3 is 18. Right? The distance between 1, 2, and 3 is 18, and distance between 1, 2, and 4, it's 10. Distance between 1, 2, and 5 is 25. Distance between 3 and 4 is 8. Distance between 3 and 5 is 7. Distance between 4 and 5 is 15. The matrix is now smaller because the total cluster reduced from 5 to 4. Now it's smaller because now our matrix is smaller because the total cluster is 5, but it's now it's reduced into 4. The smallest value here is 7. The smallest value here 7, right? 7 is between 3 and 5. Our next step is clustering. So in the next iteration, we will merge student 3 and 5 because they are the closest. Then again, the matrix will be updated. This process repeats until only a single cluster remains. Nextly, we want to create clustering. So in the next iteration, we will merge student 3 and 5. Because they are the closest, right? 3 and 5 are the closest. Then again, the matrix will be updated. This process repeats until eventually only a single cluster remains. This will repeat until eventually only a single cluster remains. Moving on, assign points to individual clusters. At the very beginning of hierarchical clustering, each data point is considered as its own clusters, right? In this picture, we can see 5 points labeled 1, 2, 3, 4, and 5. In this picture, we can see 5 points labeled 1, 2, 3, 4, and 5. Each starting as a separate cluster. Different colors. All the points 1, 2, 3, 4, and 5. Each starting a separate cluster in different colors. In initial step, was the top row. Each point 1, 2, 3, 4, and 5 is placed in its own cluster. In first step, in initial step, the top row, we can see 5 points. In each point 1, 2, 3, 4, and 5 is placed in its own cluster. This means we have 5 clusters initially. In second row, the algorithm checks distance between all points using a proximity matrix. And coming to second row, the algorithm checks the distance between all points using a proximity matrix. The two closest points are merged. Here, points 1 and 2 are merged into cluster 1, 1, 2. Yeah, the two closest points are merged in second row. Here, point 1 and 2 are merged into cluster 1, 2. The rest 3, 4, 5 are still alone. Coming to the second row, the two closest points are merged. 1, 2 are merged into cluster 1, 2. The rest 3, 4, 5 are still alone. Coming to third row, again the closest points of the clusters are merged. And coming to third row, again the closest points of the clusters are merged. The points are 3 and 5. Point 3 and 5 are closer, so they form a cluster 3, 5. In third row, the point 3 and 5 are closest, so they form a cluster 3, 5. Now we have clusters 1, 2, 4, and 3, 5. 1, 2 is one cluster, 4 is one cluster, 3 and 5 together one cluster. Now we have clusters 1, 2 together one cluster, 4 individually one cluster, 3, 5 together one cluster, right? When coming to the fourth row, the algorithm merges the next closest pair. Cluster 1, 2 merged with 4, forming 1, 2, 4. In fourth row, the algorithm merges the next closest pair. Cluster 1, 2 merged with 4. It's forming 1, 2, 4 together. Now clusters are 1, 2, 4 and 3, 5. 1, 2, 4 is a one cluster and 3, 5 is a one cluster. In the final step, in the bottom row, the last step merges the remaining 2 clusters. Which are the remaining clusters? 1, 2, 4 is one cluster and 3, 5 is the one cluster. These are the remaining clusters, 1, 2, 4 and 3, 5. In the last step, it merges the remaining two clusters. Here, 1, 2, 4 and 3, 5. Finally, we give a single cluster containing all points. Finally, we get a single cluster containing all points. Which are the all points 1, 2, 3, 4 and 5. What this means, this process shows how hierarchical clustering builds clusters step by step until only one remains. The process is usually visualized in a dendrogram. Dendrogram is a tree diagram, but here it's shown stepwise. You can cut the tree at any level to decide the number of clusters you want. For example, if we cut after the third merge, we would have two clusters, 1, 2, 4 and 3, 5. In shortly, we can say this picture is demonstrates agglomerative hierarchy clustering, where you start with every point as its own clusters. Then I attractively merge the closest cluster until only one remains. Firstly, initially, each points are its own cluster. This means we have 5 clusters initially. Secondly, the algorithm will check the distance between all points using a proximity matrix. The two closest points are merged. Secondly, it will check the distance and merging the closest points. Coming to third step in the third row, again the close points or clusters are merged. And the third step, the 3 and 5 points are the two closest, so they will form a cluster 3, 5. Now we have clusters 1, 2 is one, 4 is one, 3, 5 is another cluster. We have 3 clusters now. Now we have 3 clusters 1, 2, 4, 3, 5. In fourth row, the algorithm merged the next closest pair. Cluster 1, 2 merged with 4, forming 1, 2, 4. Now clusters are 1, 2, 4 and 3, 5. In final step, the bottom row, the last step merges the remaining 2 clusters, 1, 2, 4 and 3, 5. Finally, we get a single cluster containing all points 1, 2, 3, 4 and 5. Yeah. Meaning this process shows how hierarchical clustering builds clusters step by step until only one remains. The process is usually visualized in a dendrogram, but here it's shown as step by wise. For example, if we cut after the third merge, you would have 2 clusters, 1, 2, 4 and 3, 5. Okay. Moving on, choosing numbers of clusters. We use a dendrogram for this. It's a tree-like diagram that records the sequences of mergers or splits. Left mini panel, we can see a recap of the agglomerative process. Start with every point alone. Repeatedly merge the closest clusters and will one cluster. In left mini panel, recap the agglomerative process. Let's recap the agglomerative process in the left. The left picture, it starts with every point alone. Repeatedly merge the closest clusters and will one cluster. In the right plot is a dendrogram. In the right plot, we can see a dendrogram. It's a tree it's a tree that records those mergers and the distance, the similarity at which each merge happened on y-axis. You use this to choose how many clusters to keep. From the bottom up, x-axis label as sample 1 to 5. One joins 2 at a small height. They are very similar. 3 joins 5 at a higher height. It is 6. 3, 5 joins 4 at 10. Cluster become 3, 4, 5. Heights is how far apart the clusters were when they merged. Taller vertical link is more dissimilar clusters. How can we choosing the number of clusters? The rules shown in the slide is draw a horizontal cut where the vertical separation is largest. The number of vertical branches your line crosses, k. Vertical branches in line crosses k. Cut around height is 12 to 13, just before the tallest merge. It intersects 2 branches, case 2 clusters, 1, 2, and 3, 4, 5. Cut around height approximately 8. The intersect 3 branches, k is 3 clusters, 1, 2, 3, 5, and 4. Cut around height approximately 3. Intersect 4 branches, k is 4 clusters. That's exactly what the slide described. We can use the dendrogram. Pick a threshold horizontal line. At a meaningful distance gap and the count of intersected branches is the cluster count. When coming to moving on, note the distance of the vertical lines in the dendrogram. Note the distance between those clusters. Set a threshold distance and draw a horizontal line, generally cutting the vertical lines with maximum distance of separation. The number of vertical lines being intersected by this line gives the number of clusters. A dendrogram is a tree-like diagram used in hierarchical clustering. It records the sequence of mergers in agglomerative clustering or splits in individual clustering. It records the same sequence of mergers, it also known as it's in agglomerative clustering or splits, it's in divisive clustering. In x-axis, samples are there. It means the individual data points. In x-axis, samples are in x-axis. It represents the individual data points 1, 2, 3, 4, and 5. In y-axis, it's showing the distance, the dissimilarity or distance at which clusters are joined. Y-axis is shown as distance, the dissimilarity or distance at which clusters are joined. There is 2, 5, 6, 8, 11, 12, 14, and 16. Just think of it's a map. Just think it's a map that shows at what similarity levels different data points or clusters were grouped together. Each vertical line in the figure, each vertical line in the dendrogram represents a merge of 2 clusters. Each vertical line in the dendrogram represent a merge of two clusters. We can see the merge of two clusters in the dendrogram as a vertical line. The height of the vertical line is equal to the distance or the dissimilarity between those clusters at the time they merged. The height of the vertical line is also equal to the distance or dissimilarity between those clusters at the time they were merged. Short vertical lines represent, there are some short vertical lines in dendrogram. Short vertical lines represents clusters were very similar. There are some tall vertical lines. It represents clusters were quite different and only got merged when no closer option was available. There are two types of vertical lines are there. Each vertical line in the dendrogram represent a merge of two clusters, right? In the vertical lines, each vertical line in the dendrogram represents a merge of two clusters. The merge of two clusters. The height of the vertical line is equal to the distance or the dissimilarity between those clusters at the same time they were merged. There are short vertical lines and also there are tall vertical lines. Short vertical lines are representing clusters were very similar. Tall vertical lines are representing clusters were quite different and only got merged when no closer option was. Closer was shown available. Short vertical lines represent clusters were very similar. Tall vertical lines represents clusters were quite different and only got merged when no closer option was available. The points 1 and 2 merged at a very low distance, approximately 2. Point 1 and 2 merged at a very low distance. We can see point 1 and 2 merged at a very low distance, approximately it's 2. Yeah. The points 3 and 5 merged at a medium distance. 3 and 5 merged at a medium distance. Approximately it's 6. The clusters 3, 5 joined with 4 at 10. Cluster 3, 5 together and joined with 4 at 10. Finally, cluster 1, 2 joined with 3, 4, 5 at 14 and 15. Firstly, the point 1, 2 merged at a very low distance, approximately 2. 1, 2, very low distance, approximately the value is 2. The points 3 and 5 merged at the medium distance. 3, 5 are merged in medium distance, approximately it's 6. The cluster 3, 5. 3, 5 is a cluster. The cluster 3, 5 joined with 4 at 10. You can see in the figure the cluster 3, 5 joining with 4 at 10. Finally, 1, 2 join with 3, 4, 5 at 14 up to 15. Finally, the cluster, we can see the cluster 1, 2 joining with the 3, 4, 5 at 14 and 15. Why we need to choose the number of clusters? Hierarchical clustering does not fix K, the number of clusters. K means the number of clusters. Upfront, unlike K means. Instead, we decided later by cutting the dendrogram at a chosen height, threshold distance. Our goal is find a balance between too many small clusters and too few large ones. In hierarchical clustering, our goal is find a balance between too many clusters and too few large ones. Too many small clusters and too few large ones. A horizontal red dashed line is there. In my dendrogram figure, there is a horizontal red dashed line is drawn across the dendrogram at a chosen threshold distance. Example, here at 12. Because we can see a horizontal red dashed line drawn across the dendrogram at a chosen threshold distance. Example here, you can see approximately in 12. Whenever this horizontal line cuts the dendrogram, vertical lines becomes that determine the number of clusters. The rule of thumb is choose the cut where the vertical gap large jump in distance, because that's where clusters are mostly distinctly separated. The dashed line is drawn at distance 12. The dashed red line is drawn at distance 12. It cuts the dendrogram into two separate groups. The dashed red line will cut the dendrogram into two separate groups. We can see the cluster 1 is 1, 2. The cluster 2 is 3, 4, 5. The red line cuts the dendrogram into two separate groups. One is cluster 1. It have 1, 2. The second one is cluster 2. It's have 3, 4, 5. This makes sense because 1 and 2 are very close to each other. 1 and 2 are very close to each other, tiny distance. It has tiny distance and very close. And 3, 4, 5 are also relatively close compared to 1 and 2. 1 and 2 are very close to each other. It has a tiny distance. And 3, 4, 5 are also relatively close when comparing to 1 and 2. But the big gap between 1, 2 and 3, 4, 5 indicates there is a big gap between 1, 2 and 3, 4, 5. We can see there is a big gap. That indicates there are clearly two groups. We can see a red dashed line in distance 12. It cuts the dendrogram into two separate groups. Cluster 1, second one is cluster 2. Cluster 1 have 1, 2, and cluster 2 have 3, 4, 5. This in here, 1 and 2 are very close to each other. 3, 4, 5 are also relatively close, and it's comparing to 1 and 2. But the big gap we can see between 1, 2 and 3, 4, 5. There is a big gap. 1, 2 between the 1, 2. Just look at the dendrogram. We can see the big gap between 1, 2 and 3, 4, 5. There's a big gap. That indicates why it indicates there are clearly two groups. There is a big gap that because there are clearly two groups. That's why there is a big gap between 1, 2 and 3, 4, 5. If the threshold was set lower, set distance 8. The threshold was set lower. If the threshold was set lower, say distance 8, we would get 3 clusters. 1, 2 together, 4 individually, 3, 5 together. If the threshold was set lower, say at distance 8, we would get 3 clusters, right? 1, 2, 4, and 3, 5. If the threshold was very low, approximately 2 to 3, we would get 5 clusters. When the threshold was very low, we will get 5 clusters since no mergers would yet be recognized. When we get 5 clusters, there is no merge would yet be to recognized. If the threshold was very high, there is 3 cuts when threshold was when we setting threshold was very lower, set distance 8, we will get 3 clusters. 1, 2, 4, 3, 5. If the threshold was very low, approximately 2 or 3, we would get 5 clusters. There is no mergers would yet be recognized. If the threshold was very high, above 15 or 16, above 15, if the threshold was very high, above 15, we would get just 1 cluster. That is everything combined. If our threshold was very high, just above 15, we would get just 1 cluster. Everything combined. That 1 cluster is everything combined. Look for the largest vertical jump. In the dendrogram, we can see a largest vertical jump in the dendrogram. That's usually the natural separation. We can see a largest vertical jump in the dendrogram. It means that's usually the natural separation. Just cut just before this big jump. In this case, the big jump is between distance 10 and 14. We can see a big jump is between distance 10 and 14. Cutting at 12 captures that separation perfectly. 2 clusters. Interrupt meaningfully, we can say, does this number of clusters make sense? In our data set, like customer groups, students performance groups. Why we are using this method? Because this method is very useful. We don't need to predefine K as K-mean. Visually intuitive because it works well when we want to understand the structure of data, not just partition. In our sensitive to distance metrics, Euclidean, Manhattan, etc. It's sensitive to linkage criteria, single, complete, average linkage. It is very useful method. That's why, because we are using this. Instead of K-mean, no need to predefine K. We don't want to predefine. In K-mean, we want to predefine the K, but in this, we no need to predefine K as in K-mean. It's visually intuitive because it works well when we want to understand the structure of data. Not just partition, however, we can say it is sensitive to distance metrics, example like Euclidean, Manhattan, etc. It is sensitive to linkage criteria, single, complete, average linkage. The dendrogram in this figure, we can see a dendrogram. The dendrogram shows us how clusters are merged at different distance. In this dendrogram. The dendrogram shows us how clusters are merged at a different distance. How clusters are merged at different distances by setting a threshold. The threshold is red line. We decide how many clusters to keep. We're setting a threshold because we want to decide how many clusters to keep. The number of vertical branches cut by the line, number of clusters. In this slide with the threshold at 12, we get 2 clusters, 1, 2, and 3, 4, 5. The dendrogram, in this dendrogram, it's all about the dendrogram showing us 2 clusters, how clusters are merged at different distances. It's showing how clusters are merged at different distances. By setting a threshold, here the threshold is red line. We can set a threshold. Here it's a red line. You can see a red line. It is threshold. We decide how many clusters to keep. The number of vertical branches cut by the line is equal to number of clusters. In the slide with the threshold at 12, we get 2 clusters, 1, 2, and 3, 4, 3, 4, 5. In this section, we discussed about hierarchical clustering. I will give you some real example for hierarchical clustering. First one, we can say customer segmentation in marketing. Combining use hierarchical clustering to group customers based on their purchasing behavior, spending patterns, or demographics. Example, an e-commerce site like Amazon can cluster users into groups such as frequently buyers and discount seekers and premium customers. Deals in targeting marketing and personalized recommendations. Just another example, document or news article clustering. Hierarchical clustering is widely used in natural language processing. Example, Google News groups similar news articles together by topic. Documents are represented as vectors, and clustering helps organizing them into themes like politics, sports, or technology. Hierarchical clustering, we discussed 2 types of hierarchical clustering. And what are the importance of hierarchical clustering is, hierarchical clustering is one of the most important unsupervised learning technique. Its importance comes from the fact that it not only groups of data, but it also gives a hierarchy or structure to those groups, which makes it is easier to interpret complex data set. The importance of hierarchical clustering is we don't need of predefined clusters like k-mean. We don't need to guess the number of clusters beforehand. The dendrogram allows us to decide the number of clusters later by cutting at a different level. This makes it very flexible for exploratory data analysis. It has another importance of hierarchical clustering is visual representation through dendrogram. The dendrogram is a powerful tree-like diagram that shows how clusters are formed at each step. This visualization helps us see relationship among data points and understand the hierarchy of clusters. This example, in customer segmentation, we can see small groups merged into bigger customer categories. There are 2 types of hierarchical clustering is there. We already discussed. First one is agglomerative hierarchical clustering. Second one is The second one is divisive hierarchy clustering. What is the importance of agglomerative hierarchy clustering? It is simple and intuitive because agglomerative hierarchy clustering is easy to understand and explain. Agglomerative hierarchy clustering is very easy to understand and also easy to explain. It starts with each point as its own cluster and moves step by step until all points are in one cluster. This bottom-up process is very logical and visual. The second importance of agglomerative cluster is no need to predefine number of clusters. Yeah, like it means agglomerative hierarchy clustering doesn't require you to decide the number of clusters beforehand. We can use a dendrogram to cut at different level and choose the number of clusters later. The third importance of agglomerative hierarchy clustering is it captures small clusters well. Agglomerative clustering is a good at identifying small detailed cluster in the data. This is very useful in case like customer segmentation, finding niche groups or anomaly detections. There is, we can say another example works with the different distance measures. We can apply with the Euclidean distance, Manhattan distance, or cosine similarities. And another one type of hierarchical clustering is divisive. What is the importance of divisive hierarchical clustering? First one is we can say top-down approach. In divisive hierarchical clustering, it starts with one big cluster containing all data points, then split it step by step. This is very useful when we want to begin with the big picture, gradually drill down into smaller, meaningful groups we can get. Secondly, we can say an importance of divisive hierarchical clustering. Unlike agglomerative hierarchical clustering, when coming to agglomerative hierarchical clustering, which is good at small clusters, right? In divisive is better at finding large, broad grouping. Example, splitting customers into high spenders versus low spenders before going into subgroups. We can see another importance of divisive hierarchical clustering. We can stop the splitting at any level depending on how detailed we want clusters. It is very useful when we want both level clusters, big groups, and fine level clusters. That's subgroups. We can say another important of divisive hierarchical clustering, it's a dendrogram representation. Like agglomerative, divisive also produces a dendrogram. This helps to visualize how one large cluster gradually breaks down into small groups. Its application, when coming to divisive hierarchical clustering, there is an application in business. It starts with all customers. When coming to business, it starts with all customers. It is like a split into big groups, premium versus regular. Further split based on spending patterns. You can say the another application is text mining. It starts with all documents split by main topic and split further into subtopics. The next application of divisive hierarchical clustering is in biology. It starts with all species split into major groups, then subgroups. In shortly, we can say divisive hierarchical clustering is important because it lets us analyze data from top to bottom. Today we discussed about hierarchical clustering, right? We all I think you got my all points. I already almost covered my topic, hierarchical clustering and types of hierarchy. Of divisive dominative clustering.
Thank you so much, ma'am. Thank you. I would have to say today we discussed hierarchical clustering, and ma'am took us a wonderful session. She started off by defining it and explained how it is part of unsupervised learning. Then she also talked about different kinds of hierarchical clustering, like agglomerative and divisive. And towards the end, she also gave us some practical examples for the same. So, all in all, it was a very useful session, ma'am. Thank you once again. On behalf of my entire college, the faculty members and coordinators of FDP, I express my sincere gratitude for this wonderful session. Thank you, ma'am. So, ma'am, you can take a break, and the participants, the feedback form, the link for the feedback form will be pasted in the chat box, so you can access it and fill out the forms. Thank you once again to our resource person and all the participants who made this program a huge success. So before leaving the meeting, please fill out the feedback forms. It is a gentle reminder. We'll have to mark your attendance, and feedback forms are the way to it. Dear participants, those who have filled in the feedback forms can leave the meeting. Venkataswamy, yesterday's feedback link won't be available today. If you wanted to fill that, you were supposed to fill that yesterday itself. It won't be available today.